In the last video, we talked about the volume of a parameterized manifold. And let's just review what that was about. So you have some map from an open set of Rk. So here's, say, Rk. Let's say Rk is 2. K is 2. So you have some open set in R2, which is A, and then you have a function alpha into Rn. Okay. So let's say n is 3, and then you get some set alpha of A, and we call that Y. That's a notation, fine. Then the volume of Y was defined to be the integral over A of V of d alpha. And d alpha is the derivative of alpha, and V of d alpha, let's just recall that that is equal to the square root of the determinant of d alpha transpose times d alpha. So this is a function on A, it's defined on A, and we integrate that function. So let's look at an example. Let's say that we had a helix so alpha is a map from 0 to 2 pi to R3, which is defined by alpha of t equals cosine t sine t t. So what this looks like is so if you just don't have the z and just had cosine t sine t, that would be a circle, right? That would go circle, but as t increases, z is increasing. So when the circle makes a full rotation, that's when t goes from 0 to 2 pi, then z is equal to 2 pi. So what's going on is you start at 1, 0, 0, and then you're going in a circle, you're kind of going around, and it's going around and around like this, and it keeps going up forever. And then, if t goes to negative values, then you're just going down like this forever, and that's the shape you get. Okay. Sort of this shape. And it goes around the circle every 2 pi. Okay. But we're only looking at the part of the helix that corresponds to when t ranges from 0 to 2 pi. Okay? And so we want the length of that piece. So the volume in this case, the volume of the parameterized manifold is going to be the arc length, right? So the length of alpha, or the length of, yeah, I guess it's technically the length of alpha, or the length of the parametrized curve is, well, you would integrate from 0 to 2 pi is v of d alpha, which we know is the square root of partial alpha partial x1 squared plus partial alpha partial x2 squared plus partial alpha partial x3 squared. In other words, what we're doing, what this is the magnitude of alpha prime of t. So let's find alpha prime of t. You're going to get negative sine t cosine t 1, right? And now we need to find the length of this. That's the square root, negative sine t in parentheses squared plus cosine t squared plus 1 squared, and that gives you the square root of 1 squared plus 1 squared is 2, so you get the square root of 2. And so the length is the integral from 0 to 2 pi of the square root of 2, and that's the square root of 2 times 2 pi. Okay, so 2 root 2 pi. That's the length of the piece of the helix corresponding to t equals 0 to t equals 2 pi. Okay, let's do another example. Let's just say that you had a circle. So let's say that you had alpha of t equals cosine t sine t, but let's say you make t go from 0 to 3 pi. Well, what that's going to do is that's going to, so you're going to start at 1, 0, and then you go around counterclockwise once, and that's from 0 to 2 pi. But now you're going farther, right? You're going from 2 pi to 3 pi, and so that's going to go around the circle. That's going to go around the circle half of the way. So what do we get when we do that? Well, you can check that, okay, if I find alpha prime and then take the magnitude, I get 1. So the length of the curve parameterized by alpha is the integral from 0 to 3 pi of 1 dt, and that gives me 3 pi. So, well, that's not what we would call the length of this circle, right? We would think of the circle as having circumference 2 pi. So now we see that the length of the curve depends on the parameterization. You get the same graph, you get the same output of the function if t goes from 0 to 2 pi instead of 0 to 3 pi. But you get a different parameterization of the curve, right? And so the length depends on the parameterization, which is kind of unfortunate because we would want the length to be 2 pi and not 3 pi. So that's what happens if you restrict your parameterization. If you don't restrict, I mean, your parameterization to be 1-to-1. So typically, we will restrict to parameterizations that are 1-to-1. Meaning that we don't have different values of t with the same alpha of t. In the case of a curve, or in the case of a surface, then the point is that you don't have two different elements in the domain of alpha that get mapped to the same value by alpha. Okay, so that's the length, and then you can also find things like surface area. So let's see if I have an example. Let's say that you had the region D. So this is the region where theta is from 0 to 2 pi and r goes from 0 to 1, and then you have the map alpha that goes from D to R3, which is given by alpha of r theta equals r cosine theta, r sine theta, r. Find the surface area of D. Well, let's talk about what this object is. This is the surface Z equals R. Right? This is our x is r cosine theta, our y is r sine theta, but x and y are always r cosine theta and r sine theta. And so the new thing is just Z equals R. And what this is if you just forget, so r and theta are going from 0 to 1 and 0 to 2 pi. So let's graph that first. So here's theta, here's r. Theta goes from 0 to 2 pi, r goes from 0 to 1. So you have this region D. And then if you just forget the Z axis and just look at X and Y, then you're just mapping D to the circle of radius R centered at the origin. And you can see this if you just look at, what's going on is, let's say that you keep R to be something here, and then you let theta go from 0 to 2 pi, that's going to trace out a circle like this. And then if you take a different R, say a bigger R, that's going to trace out a circle like this, as theta goes from 0 to 2 pi. And then if you imagine all of the lines, right, you're going to get more and more circles, and then that's when you think about all of the lines, you're going to get all of the circles, and that will trace out this disk of radius 1 centered at the origin. So that's if you had alpha of r theta equals r cosine theta, r sine theta, but now you have Z, so you have r cosine theta, r sine theta, r. And what that's going to do is now Z is equal to R, right? So if you look at what happens when Z is 3, R is between 0 and 1. So let's say you look at when Z is 2/3, then that's R equals 2/3. That's the circle of radius 2/3. So you end up getting the cross sections being bigger and bigger circles. So when Z is 0, you have just the point, the origin, and then when Z is 1, you get a circle of radius 1, and then you get these smaller and smaller circles when you look at the different cross sections. And how do you know that you get a cone? Well, because so you get circular cross sections, but how do you know that sides look, like a cone? Well, one way to see this is that R is the square root of x squared plus y squared. So Z is the square root of x squared plus y squared, and then when let's say you look at the cross section where x is 0. So when x is 0, you get z equals the square root of y squared, and that's the absolute value of y. So when you slice this surface with the plane x equals 0, you're supposed to get an absolute value function. And it's the same when y is 0. When y is 0, you get z is the square root of x squared, and then that's the absolute value of x, which is also an absolute value function. So it makes sense that you get a cone. Okay. Okay. And the question is to find the surface area of this cone. So we have this surface that's, we don't want the surface area of D, we want the surface area of alpha of D, don't we? Alpha of D. That's this cone. And we saw that what you do, the surface area is the integral over D of the magnitude of alpha r cross alpha theta. And in multivariable calculus class, we would have two integral signs to indicate that you have a double integral, but I'm using the notation in Munkris's book, which has one integral sign. Okay, so now we just need to calculate this. So alpha sub r is cosine theta sine theta 1. Alpha theta is negative r sine theta r cosine theta 0. And so we now need to calculate the cross product, alpha r cross alpha theta, and that's going to be this cross product. And I'll let you calculate the cross product. You get negative r cosine theta, r sine theta, r. I guess we should put, I'll put angled brackets to indicate that I have a vector. It doesn't really matter. Okay, now we need to find the magnitude of this. So I get the square root of r squared cosine square theta plus r squared sine square theta plus r squared. And then I can factor out an r squared here, so I'm going to get r squared times cosine squared theta plus sine squared theta plus r squared. I'm assuming that that we're already all familiar with how to do these computations. So cosine squared theta plus sine squared theta is 1, so you get r squared plus r squared, that's 2r squared, and so you get the square root of 2 times r. So r times the square root of 2 is that, and then we need to integrate this function over D. And D is this rectangle. Actually, we're integrating over the interior of this rectangle. We're integrating over that open set. Remember, the boundary of this rectangle has measure 0, and that's not going to affect the integral, so we just integrate over the open set, and then that's, so if I integrate with respect to r and then theta, r goes from 0 to 1, theta goes from 0 to 2 pi. Remember that I'm using Fubini's theorem to evaluate this integral as an iterated integral. So this is the surface area of the cone. That's this. So let's calculate these integrals. So the integral of r root 2 dr is going to be root 2 over 2 r squared from 0 to 1, that's root 2 over 2. And then the outer integral is the integral from 0 to 2 pi of root 2 over 2 d theta, that's root 2 over 2 times 2 pi, so that's root 2 times pi. And that's the surface area of a cone. So those are some examples of finding the volume of a parameterized manifold, right? It encapsulates both surface area as well as arc length. And we, as this example with the circle shows, we usually want our parameterizations to be 1-to-1. Okay. So now we're going to talk about the integral. Something on the screen. The integral of a function defined on a manifold. And so we have the same setup as before. We have a map alpha from A to, say, Rn. So A is some open set in Rk. And alpha is of class CR. And you have some function now that's defined on, say, an open set of Rn that contains alpha of n. So you have some open set like this, and then you have a map alpha, which maps it to something, like this. So this is your alpha of A, and then you have a function that's defined in alpha of A, and the function is a real valued function. So the output is in the real numbers. Okay. And we wanted to find the integral of f. So the definition, the integral of f over alpha of A is defined to be the integral of f composed with A. So that's this function, right? That's f composed with A times v of d alpha. So notice that in the case when f is the constant function 1, so I have these three equal sign, the 3 bars indicate that f is just the constant function 1, then what we get is integral of 1 over alpha of A is the integral of v of d alpha, right? Because f composed with alpha is just the constant function 1, and then the integral of v of d alpha, that was what we defined to be the volume of alpha of A. And again, it's more precise to write, since alpha isn't necessarily 1-to-1 in this definition, it's more precise to write y sub alpha. So it's not just the volume of the set, it's the volume of the parameterized manifold. It's the manifold together with the mapping. Okay. So that's the formula. That's a definition. And it's a sensible definition, because in the case when f is the constant function 1, you get the volume. And in general, you're just replacing this integral. So you have a function defined on this weird thing, and then you replace it with an integral on a flat, R2 or RK, an open set. But the point is that this alpha in general will distort areas. And so there's this correcting factor v of d alpha, which takes care of that. It sort of takes that into account. Let's do an example. Let's go back to the example with the helix. So So you get alpha of t is cosine t sine t, where t goes from 0 to 2 pi. And you have the function f of x, y, z equals x squared plus y squared plus z squared. And the question is to integrate the function f over the manifold y sub alpha. Okay? So what this is by definition, it's the integral from 0 to 2 pi of f composed with alpha, so this is a function of t, times that v of d alpha, which is the magnitude of alpha prime of t. And we will usually just write dt. The dt is meaningless in this case, right? I mean, this dt is just it's just a symbol that we put. So we need to calculate, well, we already calculated that. We found that it's the square root of 2. Now f composed with alpha of t. So f of x, y, z is x squared plus y squared plus z squared. Alpha of t is cosine t sine t. So f composed with alpha of t, right? Alpha of t is this, and then this you substitute for x, that you substitute for y, that you substitute for z. So you're going to get cosine t in parentheses squared plus sine t in parentheses squared plus t squared. I'm just replacing x, y, and z with cosine t, sine t, and t. So this is going to be cosine t squared plus sine t squared is 1, and then you get plus t squared. So now we have to integrate. So this thing is the integral from 0 to 2 pi of the square root of 2. Since that's constant, I can pull it out. The integral from 0 to 2 pi of 1 plus t squared. And now this is just an ordinary integral. So you get t plus t cubed over 3 from 0 to 2 pi, and that's going to give you square root of 2 times 2 pi plus 8/3 pi cubed. And that's the answer. So, for instance, okay, one way to interpret, I mean, what exactly is this integral telling you? So, for instance, let's say f of x, y, z is the density. So let's say that this helix is like a wire, and this f of x, y, z is the density of the wire at the point x, y, z. Then when you integrate that across the wire, you get this number. The way to interpret that number is it's the mass of the wire, right? If you integrate the density, you get the mass. So that's one scenario where this has a real-world relevance. Okay, and that was an integral over a one manifold. You can also do an integral over a surface, right? That's a surface integral. And for that, so in the case of a surface, if you use r of uv, this is pretty typical notation to use r of uv instead of alpha. Then the integral of the surface, which you parameterize, is going to be, so the integral of f, say of x, y, z, so this is a surface in R3. Okay, this integral, and typically there's a ds symbol or something, is going to be, by definition, it's the integral over the region that you're parameterizing over, okay, times f of x of uv, y of uv, z of uv, so this is a function of u and v, and then times r sub u cross r sub v, the magnitude of that, dA. That's how it would be in the case of a surface. And this is probably a definition that you've seen in multivariable calculus to do an integral of a scalar function over a surface. It's a special case of what we talked about for a manifold. All right, so that's integrals of functions over manifolds, scalar valued functions. So let's just recall the step-by-step process. We needed the volume of a parallelepiped, and once we went over how to define that, then we talked about the volume of a parametrized manifold, and then once we have that, you can move on to integrals of scalar functions on manifolds. Okay, that's all I wanted to say in this video. Thanks.